Okay guys, let's take a look at today's lesson. Today's lesson is a continuation of working with vectors. So we're going to be looking at the dot product and some applications with vectors today. So more vectors, yay! Alright, so the first bullet point right here where we have horizontal and vertical components of a vector, we've been doing that for a couple of days now. We've seen that we can just use trig to do that. Are there formulas? Yes, there are formulas. These would be the formulas that would be associated with it, but why memorize those formulas when all you have to do is just draw the vector and use trig to figure it out? You can memorize the formulas if you want to, but let's talk through what is the formula. So A would be the horizontal component of our vector, and A, notice how they're using the magnitude and cosine. I mean, that's what we did yesterday, right? We just used cosine and the magnitude to find our vector. For the vertical component, notice they're using the magnitude and sine. That's what we did before the formulas, right? So these are just formalized. These formulas are just what we did yesterday. They're showing the vector in component form and in I and J. And they're basically saying if we wanted to write this vector in I and J, we would use, or like this in component form, doesn't really matter. This formula is the horizontal component, and this formula is the vertical component. And that's it. So that's really just formalizing what we're doing, by our trig knowledge yesterday. Now something new is the dot product. We haven't really talked about that before. So the dot product is an operation. We have been doing operations on vectors. We've been adding them, we've been subtracting them. This is a different kind of an operation, this dot product. Basically, what we're doing, it's kind of like multiplication. Not really. Kind of. So let's look at the process. What would we do? If vector U had a horizontal component A1, vertical B1, and vector V, see, horizontal A2, vertical B2. So those are our components. What would we do if we wanted to do a dot product between them? So the dot product of those, I would take my two horizontal components and I would multiply them. That's this right here. I would multiply them together. Then I would take my two vertical components and I would multiply them together. And then what I would do is I would just add the result of those. I would add the result of those two multiplications. Now it's important to note that the dot product isn't a vector, it's a number, it's a scalar. When we were adding two vectors together, we got another vector, right? And we were subtracting two vectors, we got another vector as our answer. Here, we're getting a number. So this is a different kind of operation on vectors than we've been doing previously. We're going to get a number. And this particular concept, dot product, is applicable in all different kinds of ways. We're going to look at two ways today. One, this dot product theorem. And actually, these two formulas right here are the same formula. This is the formula that I have memorized right here. This is the one that I use. This is just the way that the theorem writes it. Notice how they're exactly the same. What would happen to this formula if I solved it for cosine? I would get this formula, right? So these are the same thing. And this is the one that I memorized right here. This is the one that I use. What do we use it for? We use it to find the angle between two vectors. So that's a pretty important concept, a very powerful concept. One thing I need to note, though, is the vectors have to be placed in a particular way. The vectors have to be placed tail to tail for this formula to work. This formula does not work if they're head to tail. Recall when we were adding vectors, we had to have them head to tail, right? Had to. But when we're using the dot product or finding the angle between them, we have to have them tail to tail. Okay, so otherwise the formula will not work. Now, if our vector is in component form, let's look at this. If we just have it given to us in component form, is this component form, where does it originate? Is it in standard form? Yeah, right? We start at the origin and go out. So if I had vector 2, 3, wouldn't I draw it like this, right? It's in standard form. So vectors like this, they're going to be starting at the origin, right? That's where they're going to start. They're going to be tail to tail. Okay, these vectors, if you are just handed those vectors and said find the angle between, that is not a problem, because those vectors will be tail to tail. Where the problem is going to come is when it's an application problem and the vectors aren't originating at the origin. They're somewhere else. So just be aware. That's just some caution I want to put out there because it's a common mistake. Just be aware that the vectors must be tail to tail for this formula to work. So what does this do? We calculate the dot product of the two vectors and we divide that number, because it's a number, right? The dot product is a number. We divide that by the magnitude, the product of the magnitude of the two vectors, and then we do the cosine of that, right? Arc cosine of that number would give us theta. Okay, so that's how that, and we're going to practice that formula today. Okay, so that's one use of the dot product. Sometimes it's embedded in a formula. In this case, the dot product is embedded in this formula. Another use of the dot product comes with orthogonal vectors. Now, orthogonal is a fancy word. It means perpendicular. You need to know that vocabulary word, that orthogonal is perpendicular. So these things, mean the same thing. And there's a test. Sometimes maybe we want to determine if two vectors are perpendicular or not, or orthogonal. What we would do to test that is we would do their dot product. If their dot product is 0, then yes, those vectors are perpendicular to each other. If their dot product is anything else, then the vectors are not perpendicular to each other. So the dot product also serves as a test for us. That's just two of the ways that we use the dot product. There are a lot more. Okay. So questions so far on the concepts before we start on the problems. So just so that I'm pretty clear, and that is, I can't do, it's impossible to do one problem of every kind of thing that you're going to see. I know you've probably noticed that. When we get into the more advanced math, in Precal tag or in calculus, it's really impossible to do one of everything. What I strive for is to teach you the concepts so that you can apply them to other things, right? So I'm not going to do a problem that's asking you to test whether they're perpendicular or not, but if you're asked whether the vectors are perpendicular, what would you do? You would do this, right? You would do this. So it's just something that you need to recognize that you need to be able to know how to do. If you want to determine whether vectors are perpendicular, you would use this test. All right, so let's go to we have a few examples to do. So our first one is find the direction of the vector. Now this problem created a lot of confusion earlier. Let me kind of walk you through it. This problem is not in context of, let's say, bearings or direction, north, south, east, west. This is just a regular old problem that we're going to do in a regular coordinate plane. All right, we're going to measure things in our regular, normal way where, we have a regular coordinate plane. This would be my, x. I would go left and I would go up. So my vector would be like going this way. Right, this is the angle that I would do. I'm not worried. I would not work with this angle because why? Because I'm not in context. We're not going on a trip and need to do a bearing. Don't have north, south, east, west. It's just regular. So that was really confusing students earlier. This is just regular. How do we determine this angle? We rotate from the x-axis counterclockwise like we normally do. Okay, we're not in context. So if I want to find the direction of this vector, I'm going to draw it. And then let's look at its components. This is its horizontal component, so -√3. 1 is its vertical component. So that's basically what I have. So I'm looking for an angle in the second quadrant that meets these criteria. So I can really, look at this triangle. I have opposite and adjacent, so it sounds like tangent probably. Tangent could help us. So what I need, I need arctangent of -1/√3. That's what I need. I need that, and I need the angle to be in the second quadrant. So we need to think to ourselves, where would tangent be 1/√3 in the second quadrant? So we know tangent is sine over cosine, right? Sine, so the sine would have to be 1/2 cosine √3/2. You with me? So think unit circle. So that would be, and it doesn't say whether it's degree or radians. If it doesn't say, I'm going to do radians. You can do degrees if you want to. It's okay. It doesn't say. So in radians, that would be 5 pi over 6. Right? That would be the location of that angle, would be 5 pi over 6. If we wanted to do degrees, that would be at 150 degrees, right? So it doesn't specify, so you get to pick. Okay? So that's just a direction, finding the direction of the vector. Are we okay with that? Now, of course, we recognize that the direction of the vector would be different if we were in context, right? That we would say we would work with it differently, but this is just a coordinate plane problem. All right, let's look at number 2. We want to find the angle between u and v, and we also want to find the dot product u dot v. All right, so let's do that. So u dot v, let's just do that first. Let's practice our new operation on vectors. So that's going to be, and right, we're going to get a number as an answer, not a vector. It's going to be a number. So I'm going to multiply the horizontal component, so 2 times 4 plus, then I'm going to multiply the vertical components, 5 times negative 3. So what is that? 8 minus 15. So negative 7. So my dot product of u and v is negative 7. Is that okay? See how it's kind of multiplication, but really not? I mean, it has multiplication in it, but we're really not multiplying the vectors. We're doing the dot product. So now let's use our formula. They want us to find the angle between. Are these two vectors tail to tail? Yeah, they are. They're tail to tail. If I were to draw them, so I'd have one vector right here, the 2, 5, that was vector u, and then the other vector would be here, right? That's vector v. See, they're tail to tail. That's what we want to be able to use this formula for them to be like that, tail to tail. So they are like that, so let's use the formula. So the formula is cosine theta equals u dot v, which we already found, right, negative 7, over the magnitude of u. So the magnitude would be 2 squared plus 5 squared times the magnitude of v, which would be 4 squared plus negative 3 squared. Okay, we okay? So we're just using the formula. That's all we're doing is using the formula. So then I have cosine theta is going to be negative 7 over, so 25 and 4, what is that, 29. Let's see, 16 and 9, 25. So cosine of theta is negative 7 over 5 root 29. Okay, that is definitely not a unit circle value, right? We would need a calculator for that. So we would get our calculator, we would do that arc cosine, and we would put this in, right? Put this value in, so arc cosine of this value. And typically with this kind of problem, they are wanting degrees. I mean, I know it's kind of disappointing, right? We want radians, but they're kind of wanting degrees, so let's just use degrees. So theta is going to be, so I would find theta by doing cosine negative 1 of negative 7 over 5 root 29. And so theta is going to be 105.1. Oh, they did tell us to do degrees. And look, they said nearest degree. Normally we would go to the thousandths, right? But now we are going to what they said, nearest degree. So that would be this, 105.1 degrees. Okay, how is our angle between problem? We all right? Okay, the last problem we're going to work on together today is a application problem. This is where we have, let's see, we have an airplane heading due north at 300 miles per hour. It experiences a 40 mile per hour crosswind flowing in the direction north 30 degrees east. That's our scenario. They want us to express the velocity of the v of the airplane relative to the air and the velocity u of the wind in component form. So what they're asking us to do is to draw those vectors and write those vectors in component form. That's the first thing they're asking us to do. Okay, so let's do that. Get a little bit of room over here. All right. So let's work on the airplane vector first. That's kind of the easier one, right? It's just going due north. So here's my, and we're in context now. We're in context now, so we're measuring from the north line. We're going due north 300 miles per hour. So that is vector V. Now this is going to be really easy to write in component form. I like those vectors, right? So is there any horizontal movement on this vector? No. So the horizontal component is 0 and the vertical component is 300. I mean, that's my vector. So this is vector V equals 0, 300. Okay, we okay with that one? All right, let's work on vector U, the crosswind vector. It says the crosswind vector, let's see, it's going in the direction north 30 degrees east. Okay, so let's draw our north line. So northeast, right? It's going northeast. So we're going like this. And yes, we're measuring with the vertical because we're in context. Our magnitude is 40. Okay, so in order to write that in component form, we're going to have to find, our vertical and horizontal components. We had experience with that yesterday, right? We know how to do that. So let's see, if we want to find this horizontal component, we would say, let's see, so if this is 30 degrees, that's 60 degrees, right? Because that would make 90. So we would say cosine of 60 degrees equals x over 40. Now that happens to be a unit circle value. They usually aren't, but let's just, since it is, let's just play with it. So cosine of 60 degrees is a half, and a half times 40 is 20, right? So my horizontal component is 20. So we'll start U, so 20. Okay. My vertical component, so that would be sine of 60 degrees equals y over 40. So let's see, sine at 60 degrees is root 3 over 2. Root 3 over 2 times 40 would give us 20 root 3. Or you could put it in the calculator and get a decimal approximation and be fine. I'm just going to leave it in accurate form for right now. So those are our two vectors. Okay, we comfortable with that? Vector U and vector V. Part B asks us to find the true velocity, another vocab word. True velocity. If we don't know what that means, we're not going to know what to do. And all it means is to add those two vectors together. That's all it means. And a lot of times we use W to do the true velocity, but it doesn't matter. You don't have to. So what W would be vector V plus vector U. Okay, so let's add those vectors together. So 20 plus 0 would be 20, and 20 root 3 plus 300. You could write it as 20 root 3 plus 300 if you want to keep it in exact form, or you could use your calculator. Your calculator would give you 334.64 and then just more, right? We would just keep all the decimals in our calculator. 64 blah blah blah. It's 0.64. Okay, so there is our true velocity as a vector. Not too bad, right? We find the two other vectors in component form and then add them. True speed. True speed. True speed is the magnitude of the velocity vector. Right? Speed is the absolute value of velocity in function form, and when we're in vectors, it's the magnitude. So we would take the magnitude of vector W, which is the square root of 20 squared plus 334.64 squared, and that will give us 335.8 237 miles per hour. Okay, there's our true speed. Okay, we okay with that? So the last piece of information that they want from us is the true direction. Okay, so what I would do and I would recommend, this is our resultant vector. Right, this is the resultant. I would recommend that you just graph the resultant and work with the resultant vector. So we're over 20. Let's see. So here's my resultant vector. That's 20, and this is 334.64, etc. So if I want, now I'm going to want the actual direction, so it's going to be measured with the north line. And see how these directions are in north and east? And those that's how we need to give our answer. If our prompt has our directions written like this, then our answer needs to write them like that. Okay, so I really need this angle, don't I? I really need that one. I can't find it yet, but I will be able to. But I need to find this one first. Just use my triangle to find this one. Looks like tangent would work here, right? So we would do tangent theta equals opposite, so the 334.64 over adjacent. So we use our calculator, we put that in, and we get that the angle measure is 86.6 degrees. Is that our direction? Are we done? No, that is not our direction. That is not. If we were not in context, that would be our direction, but we're in context. We need to keep true to what it's telling us. So let's see, this would be north. Let's see, this is north, right? Northeast. Aren't we going northeast? And I need this angle measure. I need that one. How am I going to find that one? Just 90 minus, right? 90 minus the 86.6. So we do that. 90 minus the 86.6 is 3.4 degrees northeast. Now this is kind of significant for us and actually kind of fun. Think about how much math is involved in flying an airplane. What if the pilot really wanted to go due north? What if they wanted that and they had a crosswind that was going 40 miles an hour? Wouldn't they have to adjust? They would have to adjust to be able to do what they wanted to do. So see all of the beautiful math? So great. So at any rate, all right, so that is the lesson. Are we have any questions? Okay.